13, wow, and it's not even Friday. All right, so this is lecture 13. So we will continue to discuss a little bit about orthogonal projections and least squares. And then I will introduce the concept of orthogonal matrices to show you how they can make life extremely easy in the context of least squares. And then we will try to speak a little bit about the Gram-Schmidt orthogonalization process. And I say I will try because there are too many things we need to cover today, so you can be ready to work on your next homework. All right, so I'm going to be doing lots of jumping of the slides, and the numbers that I mentioned may not be the ones actually that stay on the slides when I revise them, but let's do our best. All right, so I'm going to go directly to the substance of the matter. Actually, before we even discuss about the slide, can one of you remind me what is the whole idea of solving AX equal to B with least squares when it's not in the column space of A? So what is the big picture? What's the big idea? Don't look on that slide. It says big idea. That's a big, small idea. So what is your big idea? So how do we approach solving AX equal to B when B is not in the column space of A, which means there is no solution to AX equal B? So what was the big idea? Don't look at that slide, okay? So let me, can I zoom it out completely? All right, so what was the big idea? Right, so basically, instead of solving AX equal to B, take the projection of B to the column space, right? And we compute it. We know how to take how to take approximations in the column space. So effectively, we were looking for AX hat, right? That's a combination of the columns, right? That's the projection point. And instead of solving AX equal B, the plan was to solve AX equal to that projection point, okay? And then we said that the big idea, if you're going to approximate AX equal to P, all right, the best point is an orthogonal projection, okay? Because the orthogonal projection minimizes the error, right? Minimizes the error. And then we use another big idea. We said if we take, an orthogonal projection to the column space, the error then is orthogonal to the column space. So in what space is the error? What is the subspace that's orthogonal to the column space? Say it again? The left null space, which means A transpose the error, and the error is basically B minus AX, right? Should be equal to 0, and from there we got the least square solution. Okay, so let's look now at the big picture with all the subspaces the way we have looked at in several of the earlier lectures. So what we have here is, let me see if this thing is going to work. So we're trying to solve AX equal to B, and the idea is this problem is not solvable because B is not in the column space. So you can think a problem with, many equations, a few unknowns, and B is not in the column space, okay? So we cannot solve it. So what we do is we say, look, let's take an approximation. Let's take the projection of B to the column space. That's that point P. But, if we do that, we will commit an error E, because B is P plus E. Think of this, a vector, you decompose it in the X coordinate and the Y coordinate. Here what I do is I take B and I write it as a vector in the column space plus a vector in the left null space, because they are orthogonal complements, right? So any vector B, all right, any vector B in Rm can be written as a point P that is in the column space and a point E that is in the left null space. We agree? Yes? All right, thank you. So, so we decompose B like this, okay? There is no approximation here or anything like that. And we say, look, this point P there, the orthogonal projection of B in the column space, is the best approximation actually I can get of something that is in the column space. And I know I have guarantees that if I, instead of solving AX equal to B, if I try to solve AX equal to P, that problem has a solution because P is in the column space. I can solve this problem. You remember it was in your homework also, you had one problem and it says, for what vectors B there is a solution, wasn't it? And the answer was, yeah, that vector has to be in the column space. Well, look, by approximating B with that projection P, this problem has a solution because P is in the column space. Now, to be able to solve this problem, you remember we assumed in the lecture 12 that the columns of matrix A are what? Because eventually we were getting the A transpose A matrix, and we said to be able to invert the A transpose A, the columns of A need to be linearly independent. Thank you. And if they're linearly independent, the null space of A is 0, contains only the 0 vector. So literally, there is a unique solution in the row space that is mapping to the projection P. And so there is a unique solution to this problem, A x hat equal to P. And that's our least square solution. I mean, the idea is very simple, right? I cannot solve AX equal B. Why? Because B is not in the column space. So what I'm going to do is I'm going to solve a close-by problem that is AX equal P, where P is the projection of B in the column space. That's the nearest point that I can consider as an approximation to B. And that problem has a nice solution, which is the least square solution, and we will see this again today. All right, we can solve this problem exactly. All right, and so pay attention again to the picture that we have written any vector B, all right, the right-hand side, as a point P in the column space and a point P in the null space. So the error, all right, the error is always in the left null space of A. Okay, so there is nothing new here, okay? So what I'm going to do is, let me go to the summary of the things we were discussing on, you know, on the previous lecture, and then I'm going to try to do one or two examples, and then we will move on from this topic. So the least square solutions, the name least squares, right? I did not say anything about it. Why do we call it least squares? Didn't see any least squares in anything we have done up to now. So obviously the least squares must be some other method that was found in somehow a different fashion that somehow turns out to be the same as what I told you. Right? Because there's no least squares on anything I told you. So you should have asked me, where is the least squares? Right? I mean, there's nothing that says least squares. So if you do not know anything about linear algebra and left null space and the projection of B on the column space and the error is in the left null space and all of these things, don't you think if somebody tells you, find an x, right, so that AX is equal to B, when B, you know, there is no solution to that problem, what you usually do is you will say, you know what, I'm going to take this square error, so you can think taking basically the first row of A times the x minus b1 and the second row times x minus b2, etc. Take the squares of this, and you say, I'm going to find the optimal x that minimizes that square error. Have you done that in your classes before? Right? That's what we call least squares. Okay? So you say, there is nothing fancy about linear algebra. You say, you know what? There is no exact solution to this problem, so let me find the x that somehow minimizes that error. And guess what that x is? Based on what we discussed about the projections of B and all of these things, what is that optimal x that you get when you minimize this error? You remember the projection of B in the column space is Ax hat. And that's what we compute. We compute what that x hat is. Can you imagine what the solution to this minimization problem is going to be? If you try by hand to minimize this square objective function, what is the solution, the optimal solution you will get? And actually, you can even see it here. I have expanded this, all right? I don't want to go to optimization theory, but you can see this is like x squared. So when you take derivatives with respect to x, you get A transpose Ax. And from here, you're going to get minus, actually here you're going to get 2A transpose Ax because it's square. And here you're going to get minus 2A transpose B when you take derivatives with respect to x. And when you want to minimize, right, you set the derivative equal to 0. So the optimal solution will be A transpose A times x equal to A transpose B. Does that remind you anything? What is the optimal solution we computed in the last lecture for x hat? Wasn't it actually this one here down there? How we have, you don't have to remember things. What is Ax? Look at this equation. What is Ax minus B? That's the error. And what is A transpose the error? It says that the error lives in what space? Ax minus B, right? Ax minus B, okay, is the error. In what space the error lives? In the left null space, and that's why we have A transpose Z equal to 0. All right, that's where we got the solution in the previous lecture. So if you take the derivatives of this with respect to x, and I'm not going to do it for this problem because it's another territory, this is a quadratic function, this is a linear, you actually get the same equations as what we got with these fundamental subspaces concepts. So basically, the idea of least squares that you learned in other courses, it is basically what we discussed here with orthogonal projections is one and the same, and that's why we still call it least squares, because effectively we're minimizing the square error. So the idea here is we cannot really solve Ax equal to B, so let's somehow find an approximate x that minimizes this error. And that solution comes to be this. Make sense? A little bit? Nope? All right. The answer is no. OK. All right. So let me see if I can do a simple example. All right. So let's suppose that you want to fit a straight line, and you have to do this in the homework. You have to fit a straight line, and I give you some. So for example, let's say that t is time, and I tell you that at time t1, I observe the quantity of interest that's b1. At time t2, I observe a quantity of interest b2. At tm, I have bm. And I want to fit a straight line in time. And the straight line obviously will be B equals C plus D times time, where C and D are the unknowns. All right? So if you write the system of equations in a matrix form, this is what the matrix A looks like. The first column is all ones, and the second column contains the times where you have observations, which are B1, B2, Bm. Okay? And obviously here, in all chances, this vector B1, Bm, it doesn't belong in the column space of this matrix A. Okay? So we really have to do a least squares approximation. So suppose you know nothing about anything we covered the last two lectures. And there's a very high chance that you know nothing about what I'm talking the last two lectures. So if I give you this problem as a homework out of nowhere and say, you know, you have done this in your undergraduate studies, go and fit a straight line, B equals C plus dt, and compute for me C and D. Give me what approaches, what are you going to do in, you know, if you have to solve this problem? So you want, you know, obviously you're going to say to me, oh, Excel does this for you automatically in the spreadsheet, right? And you just go and plot a nice straight line, but what's the algorithm? I mean, what is the approach that you will use if you have to solve this problem? I mean, give me your algorithm and I will convince you it's basically the same thing we discussed today. So how will you do this? What would be the most elementary way based on least squares? You're going to try to minimize which error? Look at these equations and tell me what error are you going to try to minimize to compute C and D? You will minimize the square error of C plus dt1 minus b1 squared plus C plus dt2 minus b2 squared, etc. And then you will take derivatives with respect to minimize that. You will take derivatives with respect to C and D, set them equal to 0, and that will give you a linear system of equations. Yes? And what you will get, it happens to be exactly equivalent with what we discussed up to now. And that's why this method is called least squares method. Okay? You minimize basically the square error from the observations from the model that you're trying to fit in these observations. And in this case, the model is a straight line. It's a linear system of equations. So in this case, you get this matrix A. And what I would suggest is, right, because it's one thing for me to say it, another for you to try it, how about if you take the formulas that we derive for the optimal solution, and at the same time you do the optimization problem, and see that you actually do get the same answers. All right, because if you don't do it, you will not know that you get the same answers. So if you do the calculations that we said in the last lecture, you compute the matrix A transpose A that you see here. And if you do the multiplications, actually you get a very nice 2 by 2 matrix. M is the number of measurements. You can see when you multiply that one row vector with this one, and you sum them, you get M. This is the summation of the times where you have observations, and this is the summation of the times squares. So this is A transpose A. And if you form A transpose B, all right, you get this. And so with this and A transpose B, the optimal X is, this is the solution we have. And so what I'm inviting you to do is go and minimize the square errors and see that you get exactly the same solution. Nothing new. Okay? So you get exactly the same solution. Okay? So actually what I have here, you know, so this is what you get with the more fundamental approach. But if you do this optimization problem and you take derivatives with respect to C and D, and I have those in the notes, actually the equations that you get are identical as the ones that you see up there. A few observations now. And actually, I don't have to do any algebra, so I just told you for this linear regression problem, this is what you get, okay? This is how the A transpose A matrix looks like, okay? Can you look at the diagonal elements in that matrix and tell me what will it take to actually get rid of the off-diagonal terms? So we said at time t1, the observation is b1. At time t2, the observation is b2. If you want to actually get rid of this, so the solution can be immediately written as c equal 1 over m times that, and d equal this divided by that. If we want to get rid of the sum of all times where we have observations, what trick can we do to the data before we do least squares? Which I'm sure you do this when you work in the lab and you try to fit a line. Have you ever done any pre-processing of your data to make the problem simple? So if somebody gives you, so when, you know, what type of observation, how will you make this summation of the times where you have observations equal to 0? What will be the trick to make it equal to 0? So obviously, you're going to have to change the variables there, but how do you change time to make the summation of ti's equal to 0? Center your time, you know, subtract the average time basically from your data. All right? So when you do that, what you actually get is you will get a diagonal matrix. And why I emphasize this? Because in more complex problems, obviously, like if this was rather than fitting a straight line, was fitting a parabola or some cubic, you know, polynomial, you will not be able to do this as simply. You will have off-diagonal terms, but it is of extreme interest to us if somehow we have least squares approximations, like what you see there, and somehow this matrix A transpose A comes to be diagonal. That would be fantastic, because if it comes to be diagonal, we will be able to actually simplify the algebra, and in principle, we will never have to invert a matrix A transpose A, especially when the dimensionality is very high. All right? So I am going to try to take advantage of this idea in the next part of the lecture today as we discuss about orthogonal matrices. So everybody is understands what we're talking. So let me give you a schematic of the two different views, and then we will move on. Okay? So let's concentrate on the view that you see on the right. So here is my vector B, and A1 and A2 here are the columns of the matrix that I am trying to solve AX equal to B. So do you clearly see that the vector B is not in the column space from that schematic? Right, I'm trying to solve AX equal to B, and let's say A has only 2 columns. So this is the column space A1 to A2. So everything in that space is generated by linear combination of A1 and A2. And the vector B is out of that space. If this is a plane, right, a plane here, B is out of that plane. So B doesn't belong to the column space. So what was the fundamental idea to solve the problem again, to get this schematic here? What have we done here? I mean, the schematic basically tells you the whole story of the methodology. So this is B. So what do? We project B, and we find this point P, all right? We find this point P, which is the projection of B in the column space. And instead of solving AX equal to B, which is not solvable, we solve AX equal to P. Okay? So that's basically the fundamental view using the column space and the left null space. And you can see here the error that is committed is orthogonal to the column space. All right? So effectively, you can write here that B minus P is such that if we call the error E right? The error E from this triangular there, E is B minus P. We agree? E is B minus P. And what is P? Is 8 times x hat, because it's a linear combination of the columns. And because the error is in the left null space, we have A transpose E equal to 0. And that gives me basically the equation I need for x hat. That's all. Okay? So that's the fundamental view. And now I want to, on the left, to give you the view that you had in mind from your undergraduate courses. So can somebody describe for me, this is the same problem, right? Basically, I'm fitting data to a straight line. And you remember my column matrix had, I had 2 columns. The first one was 1, 1, 1, 1. The second one was time t1, t2, tm, okay? So basically the same idea. I have 2 vectors, a1 and a2, but now I see here a completely different picture. Can you tell me on this picture, how do you pose the problem and how do you solve to find that straight line in this other view? So in the other view, we're going to minimize the square errors. Can you look at that plot and tell me with an equation which square errors do we minimize? I mean, if I look here, let's say at time 0, I have, this is one data point, B1 equal to 6. At time equal to 1, B2 equal to 0, that cross. At time equal to 2, B3 equal to 0. These are my data points. What errors do we minimize? I mean, the symbols are there. Can you see what, so if this is the straight line, you know, a candidate solution, what errors do we minimize? We minimize the square errors of the distances of the observations from where? Look at that picture. Look at the symbols here, E1, E2, and E3. These are the distances of my observations at the given times from where? From the line, from that approximation of the line. So the least squares problem you said here is, find me the line, so find those 2 coefficients, that the square of this error, and the square of that error, and the square of that error is minimized. And it comes out, even though the pictures are very much different from each other, the solution is the same. Okay? And look at the following thing, just, you know, so if I look at this picture, all right, you notice here it says B1 is my observation point, and I see a point P1 that's on the actual line, I see a point P2, and I see a point P3. Guess what? The values there that are computed, 5, 2, and -1, are exactly actually the values of P that I computed by projecting B on the column space. Even though I don't see any column space on the left, but those P's on the line at the given times are exactly these points. And guess what? The errors that you compute at each time where you had observations is what error points? Exactly the ones that you computed from the projection. Okay? And when you solve the least squares problem, all right, you will find actually that x hat is, you remember Ax hat is the combination of the columns where your projection is. So you will actually find that the projection is 5 times A1 minus 3 times A2. And guess what? B, the straight line, is 5 minus 3t, the same numbers. The bottom line here is, right, 2 completely different views of how you treat this problem. The answer is one and the same. The interpretation is different, all right? The answers come to be exactly the same. Of course, because we are in a linear algebra part of the course, what is the view that I like? Obviously this one. Because this is, you know, I can visualize it in high dimensions. I can do anything I want to it. and the equation, I can write it down in one line. I don't have to write any errors. I don't have to take derivatives. I don't, you know. But when somebody teaches you least squares, this is what they teach you. Okay, this is what you do. Now, will this work in high dimensions? Yeah, it will work on any setting. You will get the same answers. But I prefer this because this is so simple, right? You take the projection. The error is orthogonal to the column space in the left null space, so A transpose equal to 0, done. Okay? Nothing to memorize. Okay. With all that said, let's keep moving. So what I'm going to do is I'm going to go to slide 60 to discuss a few new things. And so we're going to discuss about projections now on an orthonormal basis. So not just projecting on the column space of some vectors, independent vectors A1, A2, but on vectors that they're orthogonal to each other. Wouldn't that be nice if somehow the column vectors of A are orthogonal? That would be wonderful. Okay, so you know what? I'm going to put all of these things up because in case we don't manage to finish things in the lecture today, this slide summarizes everything I want you to know. Literally, everything is on this slide. So first, so we're looking now on a matrix where it has columns Q1 to Qn, all right? And I am going to introduce what do I mean that these columns are orthonormal. Not just they're orthogonal, but they're orthonormal. So if you take the inner product of a Qi with Qj, where I is different from j, you get 0. So they're orthogonal. So if you take Q1 with Q3, the inner product is 0. But it also tells you that the magnitude of each of these vectors is equal to how much? If you take I equal to j, what's the magnitude of Qi? You know what delta ij is, right? It's 1 if I n equal to j and otherwise 0. So what's the magnitude of Qi? You remember the magnitude of a vector is the square root of the inner product of the vector with itself? So what's the magnitude of the Qi? 1, thank you. It's 1. And only then we call them orthonormal. The orthogonal means they're, you know, perpendicular to each other. Orthonormal means they're perpendicular to each other, but also they have magnitude equal to 1. Orthonormal. Okay? Orthonormal. So if you put all of these vectors as the columns of a matrix Q, the fundamental basic definition for that matrix Q is that Q transpose Q equal to I. Okay? So when I write the equation Q transpose Q equal to I, there is no implication here that the Q is a square matrix or anything like that. So if I have these orthonormal vectors, all right, Q transpose Q equal to I. And it doesn't matter how many I have. All right, if I put them as columns, Q transpose Q equal to I. So Q is a very special matrix. All right, Q transpose Q equal to I. Now, if by a miracle happens that Q is square, then not only Q transpose Q equal to I, but Q transpose is equal to I. Okay, so basically, the inverse of Q then exists, and the inverse of Q is the same as Q transpose. You can see it from playing with these two equations, right? So here, like Q transpose is the left inverse, here is the right inverse, but if the matrix is square, they are the same, and Q transpose is equal to Q to the minus 1, and only then we call this matrix an orthogonal matrix. So here is sort of the terminology a little bit we violated. We said orthogonal vectors don't have to have unit length, but in the literature, at least in Professor Strang's textbook, the idea there is we should only call a matrix to be orthogonal if Q transpose Q equal to I, Q transpose equal to I, and Q is a square matrix. That's when he uses the word orthogonal. So orthogonal implies basically that the matrix is square and the columns are orthonormal, and the Q inverse exists and it's equal to Q transpose. I think there's no way you can be lost, because from the context of that you'll be working on, you will know if this property is valid or not. But I want to emphasize Q transpose Q is equal to I if you have an orthonormal basis. The matrix doesn't have to be square. If it happens to be square, then Q transpose is also equal to I. So one of the things you need to be careful, don't start inverting matrices that are not squares, right? That would be a major crime, okay, a major crime. So in this case, if Q is square, then Q transpose is also equal to I. Okay, so let's take that our matrix A is an orthogonal matrix, and let's assume that we do our least squares analysis. So we're trying to solve AX equal to B, where A is really my Q matrix. All right? So A is my Q matrix. You remember, so let's start thinking, what is the least square solution X hat? Can somebody remind me from the nice formula we had? How do we compute X hat with least squares? What is the final system of equations that we get to compute X hat? Is A transpose A, X hat equal to A transpose B, correct? And what is A transpose A? If my matrix A is an orthogonal matrix, what is A transpose A? Identity. So to do least squares, I don't have to actually invert any matrix. Nice. And what is in that case the solution? Directly, you can write that X hat is Q transpose equal to B. You see that? No inversion. And what is the projection point? You remember the projection point is A, X hat, A is Q, all right? A is Q, and X hat is Q transpose B. There it is, all right? So the projection matrix here is Q transpose, okay? And obviously, if we are referring to a square matrix, Q transpose is equal to I, but I'm going to come back to that, the square matrix. The square matrix will make life trivial, okay? But we're not really interested in square matrices right now. Okay, and we're going to finish the discussion about orthogonality by introducing this Gram-Schmidt orthogonalization process. So let me define what the problem is. And then on this slide, I'm going to tell you with words how the method works, because if you understand that with words, the rest is 1 or 2 pages of algebra. So here's the idea. I give you a matrix that has some independent columns, A1, A2, A3, A5. And I tell you, can you actually use these independent columns and try to find me an equivalent number of vectors that are independent but orthogonal to each other. By the way, if they're orthogonal, they will be independent. So, you know, think in 3 dimensions. I give you 3 arbitrary vectors and tell you, use these vectors, take linear combinations so that the new derived 3 vectors are orthogonal to each other. That's what Gram-Schmidt orthogonalization is. And the way the method works is very simple, all right? So you start, so let's say that the first vector that I give you is A1, and you want to define these orthogonal vectors Q1, Q2, etc. So the first vector you take to be equal to A1. And because I want these vectors to have unit magnitude, I divide A1 by its magnitude. All right, so I take Q1 to be the first vector. Now, if I give you one vector A1, and now I have another vector A2, how do I make A2 to be orthogonal to A1? Can you give me what the idea will be? Here are the 2 vectors. All right, I fixed that Q1 is this one. Now I have an A2 at some angle. How do you make A2 to become now an orthogonal vector? What will you do? Yes. So basically, you say the second vector has 2 components, one parallel to the one that I started, and I don't need that, and one that is orthogonal. So what you really need to get this orthogonal vector to the first one, you need to remove from it its component on what vector? On the first vector. Do you see that? If you want to find, right, the orthogonal component of this vector, you have to say, I'm going to use this vector minus its component that is parallel to the first vector. Then the only thing you will get will be a vector that's orthogonal to the first one. And how will you get a third vector that's orthogonal to these two? If I have a third vector, you will have to remove its components parallel to which vectors? Or, since we talk about two vectors parallel, you have to remove its components on what plane? On the plane of the first two vectors, Q1 and Q2. Do you see that? So the idea here is you remove the components parallel to the previous vectors, all right? And then you normalize, and this is what is called the Gram-Schmidt orthogonalization process. Extremely fundamental to everything in mathematics, okay? So basically what you do is you start with a matrix A that has columns that they are not orthogonal, and you actually transform them to some columns, to some matrix Q that has orthonormal columns. And if you ask yourselves, okay, if I go from A to Q, what is actually the equation that relates A and Q? For example, when you did elimination process, you said, oh, I transform A to a lower triangular matrix and an upper triangular matrix. You remember you said A equal L times U. Here, I take A that has some arbitrary but independent columns, and I transform it to orthonormal columns Q, and then I can tell you there is going to be another matrix R there, and the question is, what is that matrix R? And here is the key idea. We started with A1, and using A1, we define Q1. Then we bring A2, and we define Q2. So Q2 depends only on A1 and A2. I did not use any of the other vectors yet. Or similarly, A2 depends only on Q1 and Q2. No other vectors. So what matrices this are going to come to be naturally is going to be a triangular matrix. All right? This decomposition, A equal QR, where Q contains orthonormal columns and R is an upper triangular, is as fundamental as the LU decomposition we get by elimination. Here is completely different scenario. We get this thing through this Gram-Schmidt orthogonalization process. I basically gave you the whole course, so the rest of the lectures, so I don't feel we need to rush on anything. So let me, there is really nothing now new to say because we are done, right? So I told you what's orthogonal already. The rest of the lecture is, the vectors, if I and j are not the same, this is equal to 0. If qi dot with qi is equal to 1, then the vectors are basically what we call orthonormal. And so that's the definition of the orthogonal matrix, all right? So Q transpose Q is always equal to I if the vectors are orthogonal and of unit magnitude. But Q transpose equal to I is only true for what matrices? For square matrices, thank you. So Q transpose is only for square matrices. All right? So when Q is squared, you have both of these, and the inverse of Q is Q transpose. OK. So in the notes, I throw lots of different Qs that you have seen and used in other courses. This is an orthogonal matrix that you can recognize immediately corresponds to the rotation by an angle theta. Okay? So if you take the inverse of that, you can immediately see it's the transpose. So you can actually do the algebra if you want to. Okay? So Q transpose is the inverse of that. And the effect basically of of q to a vector is to rotate it by an angle an angle theta. So if I apply q to the unit vector in the x-axis, it moves it to this unit vector here that has components cosine theta, sine theta. If you apply it to j, it moves it basically to minus sine of theta, cosine of theta. Okay, it moves this by an angle theta. The permutation matrices that we discussed when we were talking about elimination processes are also fall in the same category. And here is an example of a permutation matrix that basically takes a vector x, y, z and exchanges the variable and makes it a vector y, z, x. It changes the order of the variables, and you can see the first variable is going to become y, the second variable is going to become z, and the last variable is going to become x. Or you can see this in the 2D case. If you multiply this permutation matrix with x, y, you get y, x. All right, so you can verify actually that, you can actually see all the columns are they are unit vectors, and because there is only one and the rest are zeros, they're actually orthogonal, right? If you take the dot product of the first column with the second or the third, you get a 0. So the permutation matrix fits in our type of problems. Which means actually with confidence, if you have a permutation matrix, don't bother to invert it, because the inverse of a permutation matrix is Q transpose square. It's orthogonal, right? So Q inverse is equal to Q transpose. Here is another wonderful matrix that is called a reflection matrix about an axis defined by a unit vector u. So let's say that this dotted line is the vector in the direction of u. So what does the reflection do? It takes, can you look at this and give me an idea, what does this reflection matrix do? I mean, it takes the vector I, all right, in the unit x-axis, and it reflects it across this dotted mirror to a vector j. And it takes a vector j in the vertical axis, and it reflects it to the vector I. This matrix has a very weird form, I minus 2 u transpose, where u is any unit vector. Remember, u transpose is a rank 1 matrix. Okay? You can actually verify that everything we talked about orthogonal matrices are satisfied. The proof is basically on this simple line that I have here. Okay? So this reflection matrix qualifies for our Q matrix. All right. And here is an example of reflection around an axis that's 45 degrees. That's what I had before. So in this case, u is the vector at 45 degrees. And if you do the reflection, the matrix looks like this. And xy becomes yx, as you see on the graph as well. A very trivial property with this matrix is Q, okay? When you operate on vectors with Q, two things are happening. The magnitude is preserved, does not change. Can you see that? Why, if I have this orthogonal matrix Q, why is the magnitude Qx doesn't change and is the same as the magnitude of x? How do you calculate the magnitude? You remember it's the square root of the inner product. So if you have a vector Qx, what is the inner product of Qx with Qx? Is x Q transpose Qx, right? You agree with me that the length of Qx is Qx transpose Qx, and what is Q transpose Q is I, so the length is preserved. All right? How about the angles between two vectors? If you have two vectors x and y, and you try to find the angles between Qx and Qy, what happens to it? It's also preserved. I mean, you can think if you take two vectors x, y, and you rotate both of them, right? Don't expect the angle to change. The angle will remain the same. All right, and so what is the wonderful thing? We already discussed it, right? That if you do projections in the column space of a matrix that's orthogonal, basically the optimal least square solution is Q transpose B, and the optimal projection matrix is QQ transpose, okay? And I'm referring here to matrices that they are not necessarily square. So for orthogonal matrices, you don't have to do any inversion. No inversion is needed. All right, it's 11:20, and what I want to do is just finish with this equation, okay? So let's say that we have this orthogonal vectors Q1 to Qn, and I am taking a projection of the vector B in the column space of Q1, Qn. Look at this equation and tell me if the projection P that we looked at least squares looks like this. And tell me from where this equation came from. Remember that, so I'm projecting B in the column space of Q1 to Qn. So look at this expression and tell me what are these things inside parentheses. Basically, somehow, right, instead of saying, I'm going to project, I just make it even more specific. I said that the multiple of Q1 is Q1 transpose B. The multiple of Qn is going to be Qn transpose B. Does that remind you anything? So if I have these orthogonal vectors and I project them, how do you get a component of B in each of these vectors? When you project a vector in the x and y axis, how do you find its components in the x and y axis? So if I give you a vector 5, 2, and you say the x component is 5 and the y is 2, where did you get these numbers 5 and 2? The dot product with each of these vectors. So what do I have here? I have the dot product of B with Q1 to Qn. So effectively, because these vectors are orthogonal, I have been able to actually write the projection point P in this wonderful form, right? I'm decomposing this. I'm representing it in terms of Q1. And because of the orthogonality, this expression is basically nice because it allows me to compute these coefficients directly. I don't have to put and say some linear combination. I know what that linear combination is. It's Q1 transpose B, Qn transpose B, okay? By the way, I told you that the solution to the optimization problem, the projection, right, is, didn't I say that it was Q transpose B? That's what I have there. I mean, I already proved it for you, right, that the solution looks like this. I'm going to finish because it's 11:23. Can you tell me what is this equation going to tell you if the Q matrix is a square matrix? So if the Q matrix is a square matrix, means it's invertible, right? It's invertible. And the vectors Q1 to Qn span the whole space. And if they span the whole space, what this vector P becomes? If you have a vector that you can actually, if the columns are independent and span the whole space, means that B is in the column space. And if B is in the column space, what is Q1, Q1 transpose plus, etc., Qn, Qn transpose equal to? What is the projection of B, in that case, to the column space? Just B. So Q1 plus Q1 times Q1 transpose, etc., Qn, Qn transpose is equal to the identity matrix. That equation is one of the most fundamental in mathematics, basically. Okay, one of the most fundamental equations in mathematics. Okay, being able to represent things by these projections in orthogonal basis vectors. Effectively, this is what we have. Okay, so you will read more in the slides. You have to do the homework, and there will be no lecture on Friday, and I will see you on Monday.